Okay, so we're still on related rates. These are your notes for the next day. It's 3.7b. We're still talking about related rates. So to start with, over here on the side of these notes, I gave you some formulas, right? These are most of the formulas that we're going to end up using in related rates. These are formulas that we should, for the most part, try to know, right, from geometry or wherever it is. And there's some other ones that are going to come up too, but these are like the main ones for now. The one I want to kind of focus on right now is similar triangles, because this comes up quite a bit, and we have to know, what similar triangles are and how they work, right? The idea is that if I have similar triangles, which a similar triangle means that the angles are the same. So an example would be these two. They would be similar because this angle is congruent to that angle, this angle is congruent to this angle, and then this angle, it doesn't have to be 90, is congruent to this angle right here, right? So if they're similar and they have side lengths, let's call this like A, B, C, and let's call this one little a, little b, little c. If they are similar, then the ratio of their sides are equal. So what that means is I can write this proportion A over B will equal little a over little b, right? The corresponding pieces have the same, the ratio of the corresponding sides are equal, right? And so I can do this for any sides, right? I can do C over B, big C over B will be equal to little c over little b, right? And I can do anything like that for those. Any sides are proportional to each other. All right, and we end up doing this a lot. One other thing to kind of note is a lot of times you're going to see triangles like this, where you have a triangle inside of a triangle, and it's important to note that these triangles are similar because they share this angle down here at the bottom, right? They share this angle, and then due to parallel lines and stuff, those angles are also the same, and these angles are the same. So for the most part, you can see a triangle inside of a triangle, and then you have to know that this proportion thing works. All right, so that's not coming until a little bit later. For now, we're going to focus on this oil tanker problem. You can read that. You don't need me to read it for you. Basically, there's an oil tanker leaks in a circle. The circle is getting bigger. The radius is growing, and we want to know what's the rate of change of the area of the spill. I have a little animation here for you to show you what this looks like. Right, so we have a little circle with the ship in the middle, right? That red thing is a ship, and we're going to see what happens as time goes by. So as time goes by, the radius is getting bigger, right? The oil is spreading, and the area of the circle is increasing. Right, that circle is getting bigger as time goes by. Okay, so we are interested in, let's go through our process. We're talking about a circle, right? As time goes on, a circle of oil is developing. That circle has a radius r. Scientists have discovered that the radius of the spill is increasing at 2 miles per day. So the radius, the dr dt, equals 2 miles per day. The radius is currently 4, so right now the radius is 4. They want to know what is the rate of change. What do we want? They want to know the rate of change of the area of the spill. So they want dA dt. Right, so basically I need to write an equation that involves area, so that when I take the derivative I get dA dt. So let's start with area of a circle. Area of a circle is pi r squared. And there's only one variable there, so I can go ahead and just start my calculus and say, all right, let's do the derivative of my primary equation here. Right, the derivative of a with respect to t is dA dt. The derivative of pi r squared, I need to use a little power rule here. It's going to be 2 pi r times r prime, which we're going to call this dr dt, right? The rate of change of r with respect to t. And then I just need to plug in everything that I know. So we're going to plug in dA We don't know d a dt, right? That's the thing we want. That's the yellow thing that we want. We're going to plug in everything else. 2 pi, there's r, there's dr dt. R is currently 4, and dr dt is 2. And so doing all this math, we're going to get dA dt is 816 pi. Don't forget units, right? What was A measured in? A is measured in miles squared, right? Area is always squared over days. Right, time was measured in days, so it's miles squared per day. 16 pi miles squared per day. And that's that one, right? That is the answer to that problem, is right there. All right, let's go to another one. This one is a sliding ladder problem. The idea is you have a wall. You can do this many different ways. So I'm going to draw it this way. You have a wall like this, and there's this ladder leaning up against the wall like this. Right, here's a ladder. And this ladder is going to start falling down. As it falls down, the base moves out. And we want to know, the rate of change of one of those sides. Just to show you what's going on, I'm going to go ahead and show you a little video here.
Before you go on paying,
right, you can see.
So before you go on paying a person to teach you about the Keyr's sliding ladder related rate problems, take a look at this video.
One of those rates of changes. So I like to label things with things that make sense. Let's call this distance here y, because it's like a y coordinate, and let's call this piece right here maybe x, because it's like on the x-axis, right? We are given that the ladder is 25 feet tall, and it's sliding down towards the floor. What else are we given? And that's right, what do we want? The foot of the ladder is sliding away from the base of the wall at 15 feet per second. So that's the foot of the ladder is down here, right? Here's the foot. It's moving that way at 15 feet per second. So what's changing? That's x is changing, right? The distance from the foot of the ladder to the wall is changing. So dx dt is 15 feet per second. You have to think, is it positive or negative, right? Is that distance getting bigger or smaller? Well, in this case, it's getting bigger, right? Because it's going away from the wall. X is getting bigger, so it's a positive number. We want to know how fast is the top of ladder changing. So we want to know dy dt, right? That's what we want. It's the top of the ladder is here. It's moving down. We want to know how fast is it changing. You can expect that this value is going to be negative when we get it because it's going down, right? So how fast is it going down the wall when the top of the ladder is 7 feet from the ground? So at the snapshot moment where we want it, y is 7, right? And now we need to come up with an equation that we're going to be able to use to figure out everything we need. So equation, what kind of equation is going to relate all these things and tell me this, right? So you can assume that this wall was built properly and is a right angle. We have x, y, and we have hypotenuse over there. So most likely this is going to be a Pythagorean theorem problem. The reason that we can go ahead and substitute 25 here is that this ladder is a fixed length. The ladder's length will not change, right? It is 25 no matter what. Now that's not always the case for certain problems, but in this case the ladder is not changing. Like it is 25 and it's not going to shrink or grow, right? So our equation can be this, and we're looking for dy dt, so we can go ahead and start doing our calculus. We're taking the derivative with respect to time because we want to know how is it changing over time. And we're going to get down here, the derivative of x squared is 2x dx dt plus 2y dy dt equals the derivative of 25 squared is a constant, so it's going to be equals 0, right? And then our goal is to find dy dt, right? Our goal is to find this. So I can start trying to solve for that, right? Let's go and try to solve for that. Let's move let's move this 2x dx dt to the other side, like by subtracting it, and we'll get 2y dy dt equals negative 2x dx dt. And then we can divide both sides by this 2y, and we'll get dy dt equals negative 2x dx dt over 2y. And at this point, like, we have solved for what we want, but we want like a number here, so our goal is to try to plug things in. And some of this stuff we already know. For example, we know that dx dt is 15, right? This guy is 15. We also know that y is 7, right? They give us that, so I can put a 7 there. But we don't know what x is yet, and so like we need to do some other sort of math to figure out what x is. And the math that is involved there is just simply using the Pythagorean theorem with the given values. Right, I know that y is 7, and I already have the length of the ladder there, so I'm just trying to figure out, well, what is x going to be, right? So it's going to be 25 squared, and then we're going to subtract the 49 on both sides, so we're trying to solve, and we're going to get x squared equals 576, therefore x is going to be 24. Right, and now that I know x, I can, plug that 24 in where I see x to get my dy dt. So dy dt is going to be negative 2 times 24 over 2 times y, where y is 7, times dx dt, where dx dt is 15. And just do all that, right? So it's going to be negative 2 times 24 is negative 48 times 15 divided by 14, and we're going to get negative 51. So dy dt is negative 51.4, which is not making a whole lot of sense to me right now. Because that seems really fast. Feet per second. So let me pause real quick and just make sure I didn't make a mistake. Okay, no, it's not a mistake. It's just, it seems fast, but it's not that fast. So there we go. That's it. It's falling at negative 51 feet per second. Remember, always round or truncate to 3 decimal places if we're doing this, right? And don't forget your units. Okay, so let's continue with another problem. Here we have a cone, an underground conical tank. So you can imagine we are underground. Here's the ground. Underground conical tank is standing on its vertex. So the cone is kind of standing like this. Is being filled with water. Let's go ahead and draw the cone looking thing. It's being filled with water at a rate of 18 pi cubic feet per minute. If the tank has a height of 30 feet and a radius of 15 feet, so what that means is this height right here, let's call it big H, is 30, and big R, this radius of this cone, is 30. 15. Right, that radius right there, big R, is 15. How fast is the water level rising when the water is 12 feet deep? All right, so before we start that, let's go ahead and do a little animation of this cone, so you can see what it looks like. Right, you have a cone like this, and we are filling up the cone with water. I guess it's not going to show up. But anyway, you can imagine as time goes on, this water is going to get higher and higher and higher. The depth of the water is increasing as time goes on, right? It's getting, like in this case, because you're adding water, it's going to go up and up and up and up and up. And that height changes. And as you can see, the radius of like the water inside the tank is also getting bigger. Oh, here it goes. So there you go. It's getting bigger and bigger. And what's important about this is look at this triangle over here, right? You see this big height. This is our big height. This is our big radius. But you also have this little height as the water goes up, and this little radius of this other triangle. And these triangles are similar, right? So we're gonna need this in order to simplify. This is one of the examples where you need a secondary equation, right? Because you have this relationship with these triangles going on over here. All right, so let's go back to our example. We have some water in there, right? It's filling up, and this water has a little radius and a little height. It's the depth of the water if you want, right? So let's start with some given things. What are we given? We know big H is 30, big R is 15. We know that little h, the height of the water, we're calling it little h, is going to be 12 feet. And we're given that it's being filled with a rate of 18 pi cubic feet per minute. That's an important one. What is cubic feet? That's a volume. So we know that the rate of change of the volume, dV dt, is 18 pi cubic feet per minute. And what is it we want? We want to know how fast is the water level rising, right? The water level is this little h. So we're asking for what is dH dt when that h is 12. Right, so let's start with a primary equation. Primary equation is the one that is going to give us this. So in this case, the primary equation, we have a volume and we want the height. So the primary equation is going to be volume of a cone, which is 1/3 pi r squared times h. Notice how there are three variables, v, r squared, and h. That is usually a good hint that you're going to need a secondary equation, right? Because dealing with three variables, we don't have enough information for that. So we need some other information to help us with that. So what that's going to be in this case is these similar triangles, right? I have these two triangles. I have big H and big R. That's the height of the actual cone, and there's a triangle in there. And then as the water fills up, there's this little h, which is the depth of the water, and this little r, which is the radius of the water as it fills up, because it's still a circle, right? And because these are similar, I can write this proportion, big H over big R equals little h over little r, right? And big H and big R are constant, right? So this is going to be 30 over 15 equals little h over little r, which is basically 2 equals h over r. And then I can simplify this. It's going to be 2r equals h. H equals 2r. This is not actually how I want to do it. Because I want dH dt, I want this equation to be only in terms of h. So I'm actually going to solve for r, and I'm going to say r equals h over 2. All right, so, and what I'm going to do with this is I'm going to replace r here with h over 2, so that I only have a single, or I only have h's. So we're replacing that with h over 2. And now we're left with this volume equals 1/3 pi, h over 2 squared is h squared over 4 times h. So volume is going to be 1/12 pi h to the third power, right? So far we haven't done any calculus yet. All we've done is simply used our two equations to get this written, this volume equation written only in terms of h, because there was this relationship between h and r. All right, and now we can do our calculus, which is going to be, now that I have this formula and it only has h's and v's, I'm going to go ahead and take the derivative, which I should use my space a little bit more wisely over here. But let's go ahead and go over here, right? Let's go volume equals 1/12 pi h cubed, and we're going to take the derivative of this with respect to t, right? We want to find the rate of change with respect to t. This is going to give us dV dt equals this is a power rule problem, right? This 3 needs to come down. 3/12 pi h squared, right? Subtract 1 times the derivative of h with respect to t, the derivative inside with respect to t. And we get this, and then we can plug in the things that we know. We know dv dt is 18 pi. 3/12 is 1/4. This is right, pi over 4. We know h is 7. And the thing we want is this dh dt, right? That's that thing that we want. So we're going to leave that there. And then it's just a matter of solving for dh dt, right? Square your 7 is going to be 49, so 49 pi over 4. You're going to divide both sides by it. So we're going to get 18 pi equals 49 pi over 4 dh dt. And then you could like multiply both sides by 4 and then divide by 49 pi. However you want to do it. We're going to get 18 times 4 is 72 pi over 49 pi. And these pi's are going to cancel. So we got 72 over 49. This is dh dt. And it's measured in height. Height is measured in this case, feet. And time is measured in this case, minutes. So it's going to be 72 feet per minute. And that is how fast the height is changing. Let's just make sure I did that right. Yeah, okay. Another one. All right. A 6-foot tall woman is walking at the rate of 4 feet per second away from a street lamp. So we're going to draw a little street lamp over here. All right. And then there's some woman here who's walking away. She's walking that way. The street lamp is 24 feet tall. The woman is 6 feet tall. How fast is the length of her shadow changing? And then it also asks how fast is the tip of her shadow moving. So the idea here is that the light comes off this lamppost, and everything that is blocked by her body is a shadow, right? And then everything before that is not, right? So her shadow would be like here, right? This is her shadow. This red part is her shadow. And then everything else is lit up, you know, before and after that because of the light that's going off the lamppost. And the idea is she's walking away from it, and it's creating this situation. Let's see if we can find an example for this. All right, so here's that blue thing is supposed to be the man, stick man. He's going to walk to the right, away from this lamppost. Again, the dimensions here are different than mine. But as you can see the black part of the shadow down here. As he goes by, it's getting bigger and bigger and bigger. As he walks to the right, that shadow is getting longer and longer and longer. Just like when the sun goes down, right, your shadows get longer. And then the important thing to note here is that, do you see the two triangles again, right? We're going to have some more similar triangles that are involved. All right, so here we are. Let's go ahead and fill out some information. What are we given? All right, we're given, you know, let's call this big height. We'll call this little height. We know age is 24. We know that the 6-foot tall woman is walking at a rate of 4 feet per second away from the street lamp. So let's call her distance away from the street lamp x, right? That's this distance here. And she's walking away, so dx dt, that distance is increasing at 4 feet per second because she's walking away, right? And then we need to come up with some variable for her shadow length. Let's call it a. I was going to write s, but my s's look like 5s, and so let's just call it a. A is her shadow, right? And what are we interested in? What do we want? We want how fast is the length of her shadow changing. So we want dA dt, the rate of change of her shadow with respect to time. And the reason this one is so complicated is just trying to set up like what's going on here. And so the important part to notice is these two triangles, right? I'm going to go and draw them separately because it's easier, right? So you have the height of the lamppost, and then you have this big height here, which is this whole distance from the lamppost all the way to the end of the shadow. So this distance is actually x plus a. And then you have this other triangle, which is just h and a. And since these are proportional, or sorry, since they are similar, their side lengths are proportional. So I can write h over x plus a equals little h over a, right? The corresponding sides have this relationship. And then let's go and plug in the things we know. I know that this big H is 24 and it's a constant, so I can go and plug it in. And I know the little height is 6. It's also a constant, so I can go and plug it in. Let's go and do some cross multiplication on this to get 24a equals 6x plus a. So 24a, we're going to clean this up a little bit, is 6x plus 6a, or basically 6x equals, subtract 6a on both sides, you get 18a. Right, so the equation we're using here is 18a equals 6x. And since we want dA dt, we're going to go ahead and take the derivative of this with respect to time. What's the rate of change with respect to time? And we're going to get 18 dA dt equals 6 dx dt. Right, and our goal here is to find dA dt, so we divide both sides by this 18, and we get dA dt equals 6 over 18 dx dt, which is 6 over 18 is 1/3, right? So let's go ahead and just replace this as 1/3. And we know dx dt, so dA dt is going to be 1/3 dx dt. Dx dt is 4, so dA dt is going to be 4/3, and just don't forget about your units. A is measured in feet because there's that shadow length, and then this is time is measured in seconds. So 4/3 feet per second is the answer to the first one. And then the second one's a little bit trickier. It's asking how fast is the tip of her shadow moving. So that's this piece right here. And the trick to this is, well, it's moving, like the x piece is moving at dx dt, the a piece is moving at dA dt, the tip is moving at both of those combined. So the tip of the shadow is moving at dx dt plus dA dt, which is simply 4 plus 4/3, which is 12/3 plus 4/3. So 16/3 feet per second is how fast the tip of her shadow is moving, right? You just have to add the rate of change of her distance from the lamppost to the rate of change of her shadow. You add those two together and you'll get the rate of change of her, the tip of her shadow, how fast the tip of her shadow is moving. All right, let's finish this off. One last problem, problems with angles. So Sophia is sitting on the ground, right? We're seeing some person on the ground. 10 feet from the spot where a hot air balloon is taking off. So there's 10 feet, and then there's like a hot air balloon taking off here. Right, there's a hot air balloon. It's going up because it's taking off. Oh, sorry, it's about to land. Read the problem. It's going to land, so it's going down because it's landing. She is watching the balloon as it travels at a steady rate of 20 feet per second towards the ground, so it's going down at 20 feet per second. If theta is the angle between the ground and her line of sight, so this is theta, like, right, is the ground, and here's her line of sight. At what rate is the angle changing at the instant the balloon hits the ground? So let's go ahead and put some variables in here. Let's call this x. Let's call this distance y. What are we given? We're given that the y distance, the up and down distance, the rate of change, dy dt, is negative 20 feet per second. Why negative? Because it's going down, right? And the balloon is, that distance is shrinking. All right, and what do we want? We want the rate of change of the angle. So the angle is theta, so I want d theta dt. That's the thing I want. So I need to come up with some sort of equation that relates two sides and this angle, right? Well, that's a trig identity. So what like if this is the angle, what trig identity is going to relate the y and the x there, right? That's opposite over opposite over adjacent, right? Which one relates opposite over adjacent, or adjacent over opposite, I guess you could say too. Well, it's going to be tangent, right? Tangent is opposite over adjacent over hypotenuse, which in this case is x over y. Tangent of theta is x over y. This is our equation, right? And we want to know d theta dt, which means I need to take the derivative of this with respect to time. Before we do this, in this case, it's easier to think like, are any of these constants? That way I can avoid quotient rule on this x over y. So think about, are any of these things constant, like not moving, not changing at all, right? Well, think about this distance right here. Is that changing? No, right? Because she's just sitting there. So I can actually, in this case, replace x with 10. Why? Because it's not changing. It will be 10 the entire time. Okay, so now we're going to go and take the derivative with respect to time, the rate of change with respect to time. The derivative of tangent is secant squared theta times d theta dt equals 10 over y is the same as 10y to the negative 1, so it's going to be negative 10y to the negative 2. And let's go and go up here. This is going to be secant squared theta d theta dt equals negative 10 over y squared. And we could divide both sides by secant theta to get d theta dt equals negative 10 y squared secant theta. And so now we want to plug in the things that we know. Oops, and I forgot something, right? I forgot dy dt. Let's just be a dy dt up here, right? When you take the derivative of the y, you get this dy dt, so that's up there. Now we need to plug in the things that we know. I know dy dt. I know y. Do I know y? And I can figure out y. And oh, because as it hits the ground. Okay, so I can figure out y because it says what is the rate of change as the balloon hits the ground. So as soon as it's hitting the ground, y is going to be 0. Yes, so y is going to be 0 at that point.